let me start the recording here. Okay, we're continuing in session 4.6 and we're looking at optimization problems. Okay, we already looked at a few optimization problems on Monday, and we're going to look at a few more today. So let me give you a moment to copy this example down, and very good. Okay, all right. So, all right, in this problem, we want to find the dimensions of the rectangle of largest area that has its base on the x-axis and its other two vertices above the x-axis, and the other two vertices are above the x-axis and lying on this parabola, y equals 8 minus x squared. So, you know, there are a lot of problems in optimization. You know, the book has a lot of problems, and you know, I'm giving you some standard problems, but I'm trying to give you problems too that are like you'll see you'll see in the homework if you've not already. You know, problems that are applicable to real life. And this problem I regard as sort of an architectural kind of problem. Okay. So what's the first thing that we should do to solve this problem? I mean, what do we need to start the problem off? That's right. That's right, Lynn. We have to draw it. We have to draw it. Okay. And so, well, let's make a drawing. May I move to the next page? Is everybody done copying the example down? All right. Very good. Very good. All right. So I go ahead and draw the parabola y equals 8 minus x squared. And, you know, to draw it, of course, I mean, I know the parabola opens downward and it has a y-intercept of 8 here. And I need to find the x-intercepts of the parabola so that I could, you know, draw the parabola reasonably. And if I take 8 minus x squared and set it equal to 0, it turns out the x-intercepts for the parabola are 2 root 2, 0 and negative 2 root 2, 0. Okay, that's what those intercepts are. And 2 root 2 is about 2.8. Okay. So let me give you a moment to copy the picture down. Let me just see here one thing. Okay. Now, what I've done also, in addition to drawing the parabola, is, you know, there's a rectangle, and the rectangle here, maybe I'll draw it in red. The rectangle has as its base this x-axis. Okay, that's the base of the rectangle, and so, you know, you have there are 4 vertices to the rectangle. Well, 2 of the vertices are down here, but then the other 2 vertices of the rectangle are above the x-axis and lying on the parabola. Okay, so this means then that the height of the rectangle is going to be given by y, where y equals 8 minus x squared. Okay, because we agree that the y determines the height, the value of y, and that value of y is equal to 8 minus x squared, because the vertices here on the top part of the rectangle lie on the parabola. And then, of course, the rectangle has on its base the x-axis. So, but like the way I've drawn this, and maybe I should add this to the little drawing here. I mean, this here is a distance x. Okay, that's a distance x. So I'm defining my x to go from the origin, you know, to the right. And so that means then that the base of and x is greater than 0, of course. The base is 2x. I think, let me see here. Hold on, I'm trying to, I saw the chat. I'm trying to get it. I don't know why I can't get it. Hold on, class. Attendees. You have to forgive me. For some reason, I'm having trouble getting into seeing the chat. What's being chatted? I don't know why. Let me just say hi and see if I can get the window open. Hi. Can you chat that again? The person that asked that question. Somebody asked a question. I think they asked, could the base just be x? Well, it's easier to define x. You know, of course, in this scenario, x is greater than 0. So I'm just defining x to be yeah, all right. Ian says, could you define the entire base as x? Let's see. Well, I think that would be hard because, see, this vertex here, right there, that I'm highlighting, has an x coordinate. So it's natural to if you want to like think about, you know, x coordinates, and you have to think about x coordinates because y is defined in terms of 8 minus x squared, where x is the x coordinate. So and the way I have my x here is that x is positive. So the base, which is a positive, you know, the length of the base, which is positive, is 2x. I think, Ian, you almost have to do it the way I've done it. I'm not sure if it could be done any other way. Okay, does that make sense? Okay, good. Okay, well now, of course, what we're interested in is we want to find the rectangle of largest area. So we're going to be interested in maximizing the area. Well, the area of a rectangle is, of course, the base, which is 2x, times the height of the rectangle. And so you're going to get 2x times 8 minus x squared, which is 16x minus 2x cubed. And that's the expression for the area of the rectangle. And we wish to maximize the area of the rectangle subject to this constraint that x would have to be between 0 and 2 root 2. And that's because let's see here, one moment. That's because the x-intercept for the parabola here is 2 root 2. Okay, how is the height equal to, how is the height, sorry, one moment here. How a person asks, how is the height equal to 8 minus x squared? Well, that's the function of the parabola. That's right, Lynn. Here's the height right here. There's the height, and the height, the height would be would like this point here. This point right here. Okay, its y coordinate would be the height. And so, but that point is on the parabola, and the equation of the parabola is y equals 8 minus x squared. Okay, is that comfortable? Are there any questions so far? All right, let me just, okay, very good. Let me just see here. Okay, now I got my chat thing back. Now, okay, and Trevor's good. All right, now, okay. All right, then what do we want to do with our function a of x? You know, a of x is equal to 16x minus 2x cubed. What do we want to do with that function? Find its derivative. That's right, because if we want to maximize a function, we have to find its derivative. Okay, I'll move to the next page if we're good. Are there any other questions before we move forward here? All right. All right. Very good. Well, then let's move forward. So the derivative of your area function is going to be 16 minus 6x squared. It's easy to take derivatives of polynomials. And we want to find out where the derivative of our area function equals 0, because that's going to allow us to find the critical value. Right? We have to find the critical values. So I'm going to just set my a prime of x, which is 16 minus 6x squared equal to 0, and I'm going to solve for x. Okay, so I'll give you a moment to copy this. You let me know if you have any questions. Okay, so turns out that x will equal 2 times the square root of 2/3. That is a critical value of our area function. Now, just I put down the approximation. 2 times the square root of 2/3 is approximately 1.63. Of course, I'm not going to use that approximation in any of my computations yet, but I just wanted to give you a feel for how, like, what x would be. So that the most x would be 2 root 2, which is about 2 root 2 is about 2.8 approximately. So, all right. Now, the question that we always have to ask when we have, remember again that x is between 0 and 2 root 2. In this interval, we found, in 2.2 is approximately 2.8. So we always have to ask ourselves when we are maximizing or minimizing a function over an interval, a closed interval, could the maximum or minimum, could the maximum area be at one of the endpoints? Okay, we have to ask that always when we are maximizing or minimizing a function. I mean, I want to say it more clearly. We're trying to find the maximum value. That's an extreme, the absolute maximum. That's what we're trying to find, the absolute maximum area. So could it be possible that the area would be maximized at one of the endpoints in our closed interval? Or is the area maximized at x equals 2 times the square root of 2/3? So because we have a closed interval, we have to check the area, the value of the area, at each of these endpoints. And a lot of times it will be, you know, well, we just have to do it, and you'll see why. But let's go ahead and check that. So let me go to the next page here. Well, let me ask you this: if x were equal to 0, looking at our picture, our base is 2x. If x were equal to 0, would we have a rectangle? I mean, if x were equal to 0, what would the area of the rectangle be? We would not. I mean, what the area would be 0. Good, good. It's a line. That's right, Ian. That's right. What about if x were equal to 2 root 2? What if x were equal to 2 root 2? Would we have a rectangle? Okay, we would not. We would not. We would have a line segment. So if x equals 0 or 2 root 2, you're going to get a line segment. And what I've done here is I've said, okay, well, suppose x equals 0. A of 0 computes to be 0, and this corresponds to a line segment. Okay, I kind of drew a fat line segment here just so you get the idea. But that's going to be your line segment. Okay. On the other hand, if x equals 2 root 2, the area there is also going to be 0 because you're going to that would be a box. That would be a horizontal line segment. There's no height to it, just width. But there's no height, and so the area equals 0. Okay. So let me just write that in. Okay. So clearly then, the area is not maximized at either of the endpoints x equals 0 or x equals 2 root 2. Let me give you a moment to copy this down, and then I'll talk a little bit. I want to make sure I'm, pacing myself well, and we'll talk about the little picture here and stuff. Okay. Okay, so clearly the area of this rectangle is not maximized at these endpoints x equals 0 and 2 root 2. And as a rule, when you are maximizing, when you're trying to find the absolute maximum or minimum of a function over a closed interval, you need to check the endpoints. You need to check the endpoints because your function could look like this. Now our function does not look like this. What I'm boxing here in red, our function does not look like that. But suppose the function did. You could have the case where yes, 2 times the square root of 2/3 is the critical value because the derivative is equal to 0 at that x value. You know, you can see the tangent line has a slope of 0 at that point, but it's not the absolute max. The absolute max would be up here at the right endpoint 2 root 2. Now, of course, this is not what's happening for our example, but I'm just saying it can happen. It can happen in different kinds of problems. Okay, and so you have to always check for that. Okay, does that? So, you know, this is, of course, in case your function looks like that, but, you know, AX does, you know, note, I'll make a little note here. Our area function does not look like that function there. Okay. Okay. All right. Okay, so are there any questions? All right. Well, now one thing is the next question we want to ask ourselves, and it's obvious that the area of the rectangle is maximized when x equals 2 times the square root of 2/3. I mean, it's the only possibility, right? The only possibility. But we should be able to use calculus to confirm that. And I'd like to show you how to use calculus to confirm that on the next page. All right, so are we good? May I go to the next page? Okay. John asked, what's the function of the graph? What does A of x look like? You know, John, I haven't really graphed it because but I know, well, the A of x function is here. So it's it's a cubic polynomial, but I don't really need to graph it. I can use calculus to confirm what I need to confirm. But you see the calculus. Oh yeah. So the question now is our function a of x maximized then at x equals 2 times the square root of 2/3? And what I'm going to do is I'm going to look at the second derivative. So the first derivative here, as you know, a prime of x is 16 minus 16x squared. The second derivative then, a double prime of x, would equal negative 32x. And because, why would I want to do this? Why would I do this? Because of this. Our second derivative is going to be negative over the interval from 0 to 2 root 2. Okay, which means that our function a of x is concave down on the interval from 0 to 2 root 2. Okay, so I mean, basically the situation is hold on here. I mean, you have basically a function that maybe looks like this. Okay, maybe it looks like this. Let me see if I can. Again, I haven't graphed it. I mean, I can graph it on my calculator, but one moment. But it isn't like I have to. I want to kind of get away from using graphs. No, well, oh, 6. Yeah. Hold on. Class, there's an error here. Thank you, Kelvin. Good catch. It won't change what I'm doing, but this 16 should be a 6. Okay, 16 is a 6. And so we're going to get negative 12x. Okay, so thank you, Kelvin. Thank you. All right, and let me fix that on my notes too. I'll do that right now. So here's really what I'm trying to sort of get at here. Okay. So if I have a concave down function, okay, here's just some concave down function. Okay, and here is 2, hold on. Here is 2 times the square root of 2/3. Here. Okay, and I'm not even gonna, I'm gonna be a little careful here how I draw this. I'm just I'm just, you know, it's just a little picture, okay? A little picture. My function a of x between hold on. Let me do this again. No, I don't want to do it again. I'll draw in a moment. I'm gonna show you what I'm getting at here. See, these are the kind of things where in a classroom on a board I could really, you know, do it quickly. But here it takes a little more time. So I've not drawn my a function I've not drawn it on the calculator, okay? But I know that the at 2 times root 2/3, I know that's a critical point for my area function, meaning that there is either a maximum or a minimum. The 2 times the square root of 2/3 either maximizes or minimizes the area. I'm going to say when x equals 2 times the square root of 2/3, my area function is either maximized or minimized. But the area has to be maximized because this function a of x, gosh, I can't get this thing. This function a of x is concave down, right? It's concave down over the interval from 0 to 2 root 2. The second derivative of the area is negative. So the area function's concave down over the interval from 0 to 2 root 2. Well, that means then that at my critical value, 2 times the square root of 2/3, the area function is maximized. Okay, does that make sense? I mean, it's a lot quicker to do that than to draw a graph of the area function. I'm using calculus to verify things. Okay, thank you, everybody. Yeah, we're using calculus. I mean, anybody can graph a function, right? I want to use calculus. We want to use calculus here. And so the rectangle of maximum area would have dimensions then. Well, the width was 2 times x. So that's going to be 4 times the square root of 2/3. And the height y was 8 minus x squared. And that's going to be then 16/3. It turns out it'll be 16/3. And so I think of this as like an architecture kind of problem. I mean, imagine an architect's designing a, in the design they have a parabola. Okay, maybe I don't know. Maybe it's I don't know. I don't know what kind of house, but anyway, the backyard there's a parabola there, and maybe they want to have a pool, inside the parabola. Maybe it's like a parabolic fence or a parabolic boundary for the pool, and then the pool they want to make rectangular. Well, you want to have the maximum area for the pool. You would want to have your width to be then 4 times the square root of 2/3, and of course the units are meters, right? And the height would be 16/3 meters. And height meaning, like the length. I'm talking, length and width. Okay. But let me see. So that would then be how you design your pool. Okay. So it would be 3.26 meters across, and it would be 5.3 meters go lengthwise. So, and if maybe it isn't a pool. Maybe it's one of those. You ever see on the television those ads for the pools where you can swim in them? They have the jets going, and you can swim, and you don't need a big pool to swim. It's like a little pool, but it has jets so that you can swim and not like move. How many have seen that kind of thing on the? Okay, so hey, maybe it's one of those kind of pools, but it's an architectural kind of problem. And I know that architects, I know at some schools they have to take calculus 1 and 2. All right, are there any questions before we move to the next example? Okay, let's move to the next example then. Okay. All right, so I'm trying to do a variety of examples with you, and in your homework there are, in the exercises, there are exercises that are going to resemble the ones I'm showing you, but then there will be other exercises. But at least some of those exercises have help aids, okay? But hey, you might have to figure out a few on your own, right? I mean, you're training to be engineers, so, but I'm trying to give you a lot of support here. Because how many find these problems to be a little bit challenging sometimes? I don't like to use the word difficult. I like to use the word interesting. Well, they're engineering type problems, right? They're interesting, and this is engineers solve real world problems, and that's what you're doing. All right, so let me give you a moment to copy this down. Okay, so here we have a piece of wire 10 meters long that's cut into two pieces. One piece is bent into a square, and the other is bent into an equilateral triangle. Okay, so all right, I'm taking a piece of wire, cutting it into two pieces. Then I'm going to bend one piece so it's into a square, and maybe a machine will do that. And the other will be bent into an equilateral triangle. Okay, so we want to find out how should the wire be cut so that the total area enclosed is a maximum, and then how should the wire be cut so that the total area enclosed is a minimum. By total area enclosed, I mean the area enclosed in the square and the triangle. Let's see, Ian says nominally if they want the most area, shouldn't they just not cut it and make it a circle with diameter 10? Well, the diameter couldn't be 10 meters because the wire itself, your comment's an interesting one, Ian. This is your wire. This is your wire, and it's 10 meters. Oh, I see. You mean circumference. Well, you know, what Ian's saying, why not just take your wire and, you know, bend it into a circle? And would that give maximum area? Would this give you maximum area? Intuitively, I think it maybe would, but again, I'm not sure. Without calculus, I wouldn't know for sure. I mean, that would be a very interesting problem to see if a circle would have the most area possible. You know, a circle with a 10-meter circumference. But in this case, though, maybe we don't want to do that. You know, maybe we're running a company and we're making squares and triangles with our wire. Okay, so you know, we have to work with what we have to do. Maybe we have a client that wants this. That's right, Lynn. Do what the customer wants. So how would you start this problem off? How would you start this problem off? What would be very helpful to have? Well, indeed, Joe, make a square and a triangle. But even before then, I'm going to draw my wire and I'm going to make a cut. Okay, so let me show you that on the next page. Are we good here? We'll move forward. I really like the very good participation today. Okay, let's go forward. So, okay, what I do is I make a picture. Okay, here's my 10-meter wire, and I'm gonna cut it into two pieces. The first piece has distance x. The second piece would have to have distance 10 minus x. This is how you have to do the problem, okay? So you have to, like if you had this problem on exam 4, you would have to do it this way, okay? You need a variable in there. Just like with the baseball diamond problem, you need to have a variable in there. You know, same here. You got to have a variable. We don't know how. I mean, we don't know where we're going to make the cut. You know, we don't know where that cut's going to be, but it's got to be somewhere. So we'll call the first piece of wire x, and then the second's 10 minus x. So what I'm going to do is I'm going to take the piece of wire x meters long and bend it into a square. Well, the square would have to have sides then of x over 4, because you know, note that 4 times x over 4 equals x. So the perimeter of the square has to equal the length of my wire. And my wire is X meters. All right, are there any questions on that? Let me know. All right, well, the other piece of the wire is the 10 minus X part, 10 minus X meters, and we're going to bend that into an equilateral triangle. Well, here's the equilateral triangle. Here it is. And so equilateral triangle, every side has the same length. So each side would have length 10 minus X over 3. Because if you take 3 times 10 minus X over 3, okay, if you do that, you'll get 10 minus X. And that's how many meters you're using of wire for the equilateral triangle. Hold on, Sebastian has a question. Would we get the same answer if you would? So Sebastian's saying, what if we use the 10 minus X portion of the wire, the 10 minus X meters, to make the square, and X meters to make the equilateral triangle? Yes, you would have to get the same answer, Sebastian. And I know why you're thinking that. You're thinking it might make it a little bit easier. Maybe it would. I just, did it this way. Now, we need to find the areas of the square and the equilateral triangle. The square is no problem. Area of a square is length times width. But the area of the equilateral triangle, well, area of a triangle, what is the area of a triangle? What's the formula for the area of a triangle? Right, 1/2 base times height. Good, Nicholas. Good, Joe. So I need to find the height here of, hold on. I need to find the height of my equilateral triangle. Well, in order to do that, I have to make use of a fact that I learned in trigonometry. We know that, whoops, hold on. We know that in my equilateral triangle, this angle has to be 60 degrees. All the angles have to be 60 degrees. But just looking at the right triangle here, the right triangle there, because again, I'm trying to determine the height, of my equilateral triangle. So looking at that right triangle there, I'm cutting that equilateral triangle, I'm bisecting it in two. And this right triangle, that angle's 60 degrees. What's this angle going to be here? What's this angle going to be right here then? What's that angle have to be? It has to be 30 degrees, right? And so I have a 30, 60, 90 right triangle here. And I know that 30, 60, 90 right triangle, that the sides are in these proportions. Opposite 30 degrees is 1, opposite 60 degrees is √3, and the hypotenuse is 1/2. Okay, how many have seen this triangle in their trig class? It's something you should have seen. It's very common, very common. All right, very good. Thank you, everybody. And so now I'm able to get the area, okay, of the square and the equilateral triangle. So this is the square, length times width, right? And then this part here is the area for the triangle. Area of the triangle is 1/2 base times the height. Now, I'll just comment here. The half is there. The base, based on the picture, is 10 minus x over 3. But then the height of this hold on. This height here, well, for the 30, 60, 90 triangle, the I want to say this the right way. You can the height is going to be. Oh man, let me get this. The height is √3 for a triangle with base 1. So the height √3 is like √3. Hold on. The height for my right triangle is √3 times 1. Okay, for this right triangle here. Well, then if we go to the triangle here, the one I'm using in the problem, I don't have a 1 for my base. I have the base here. This is the base. If that's going to be 1/2, hold on here. One moment. One moment. Right. So this height. Okay. So let me just. I'm talking here about. This is the height here of my equilateral triangle, because how am I getting that? Well, let's go to my little triangle down here, my 30, 60, 90 triangle. Okay, there's √3. Here's 1. √3 is simply √3 times 1. So you can get the height of the right triangle, of this 30, 60, 90 degree right triangle, by taking the height would be equal to, I want to say it, I'm sorry, I'm not saying this the way I want to say it. In my equilateral triangle here for my problem, this right triangle here, the sides are in proportion to my 30, 60, 90 degree triangle. Okay, so for my 30, 60, 90 degree triangle, the height √3 is equal to √3 times the base 1 times that leg equal to 1. Well, my leg here, right here, is going to be 1/2 10 minus x over 3. That's how I get the half times 10 minus x over 3. And I multiply that by √3 to get the height for my equilateral triangle in the problem. And that's how we get then, this second part. Are there any questions on that? Any questions on that? You have to let me know. Well, Zoe, you're right. I can, so now I write a of x. I write it, so it equals x squared over 16 plus √3 over 4 times the quantity 10 minus x over 3 squared. And I could expand this part out, but what am I going to want to do with my area function? What do I want to do with it? I mean, what do I want to, in order to maximize the area, I want to take the derivative. So I kind of like the area function as it is for taking the derivative. But you could expand it out, use FOIL. But if you use this as your area function, when you take the derivative, it's not too hard. Because all you do is you use the chain rule here and the power rule. See? This is to the first power, by the way. This is power 1. Run here. So it's raining a little bit out there. So it's good we're at home doing our remote learning. Some days remote learning's, I mean, I'm kind of getting used to it, but I miss seeing students in person. But the chatting helps a lot, like on the chat line when you ask questions and so forth. It really helps a lot. And I hope it helps you too. So a prime of x, what I do is I just write it and simplify it until I get that a prime of x, the first derivative of the area function, equals x minus 8 minus 10 root 3 over 18 plus root 3x over 18. Okay. Okay, are there any questions on that? Well, what do we do now? What do we do now? We've taken the first derivative of my area function for a reason. What do we need to do now? Okay, find the min and max. And what do we need to, that's right, Ian, and what do we need to do with this derivative function? Find the critical values. And how do we find the critical values? Good, we set the first derivative equal to 0. Okay, and so that's what I'm going to do. So may I move to the next page? Are we okay? Are there any questions? Okay. Well, so a prime of x, I combine the two terms. Well, what I mean is two terms from the previous page. Oh, well, actually, hold on. In the previous page then, a prime of x, I write this way. I combine my x terms. And okay, and then I'm going to set that equal to 0, and I'm going to solve And, you know, it's just being, you know, I'm going to combine the two fractions here. And the common denominator is 72. And, I mean, really, I think, you know, let's make sure people are comfortable up to this step here. This here isn't anything. All right, and to get x by itself, I multiply this equation here by the reciprocal. And so I get here, and the 18 and the 72 reduce to 4 and 1. And so x will equal 40 root 3 divided by, I think I have another typo here, over 9 plus 4 root 3. One moment. Hold on. One moment. Yeah. I mean, the math's right. It's just I need to have a 4 here. So let me fix that right now. Very happy I caught that before Kelvin. Kelvin would have caught me on. Kelvin, you would have caught that, right? I caught that before you. Okay. Yeah. So that's 4 root 3. Okay, and let me fix it on my notes too. Now that's going to probably, let me see here. That decimal, let me check that decimal. This decimal should be now 4.35, I believe. Okay, and again, we're not going to use the decimal yet, but I just want to kind of get a feel for it. So what it's telling us is that the critical value occurs when you make the cut 4.3 at 4.35 meters. Okay. So the question is, the first question was, all right, you know, we have this critical value now. Okay, 40 root 3 divided by quantity 9 plus 4 root 3, which is, as a decimal, is approximately 4.35 meters. And would cutting the wire at 4.35 meters, you go along the wire, and then when you reach 4.35 meters, you make it there. Would that maximize your area of the square and the equilateral triangle? Now, it's tempting to say yes, right? It's tempting to say yes, but the answer is going to be no. Let me show you why. Yes, we have a critical value. We have a critical value at x equals 40 root 3 divided by 9 plus 4 root 3. But does it maximize the area? Well, to answer that, what we do is we look at the second derivative. The second derivative, okay, is the derivative of the first derivative. So the second derivative is going to be equal to a constant, 1/8 plus root 13 over 18. And that's going to be greater than 0 always. Let me see. Oh, yeah, that should be root 3 here. Hold on. Good catch. Oh, man, Ian caught me there. Ian caught me. All right, good catch, Ian. It doesn't change anything. But this here, let me just, this here should be a 3. So that's a 3 there. And this is a 3 also. That works. Okay, that's a 3 also. So now x is between 0 and 10 because the cut has to be somewhere along that wire, and the wire is 10 meters long. But the fact is, because the second derivative is positive, okay, the second derivative is, hold on. Let me also, that x there. Right, 40 root 3 over 9 plus over 9 plus 4 root 3. Okay, so because the second derivative is positive, okay, over my interval from 0 to 10, that means that my area function, whatever it looks like, whatever the graph of it looks like, is concave up. It's going to be concave up over the interval from 0 to 10. And so that means that you can't maximize the area, but only minimize the area. Because if your area function is like this, if this is your area function, okay, I mean, it's concave up, right? So if this is your area function, okay, from 0 to 10, it's concave up everywhere. And then, here, right here, is your critical value. Okay, man, I don't want to write that in, but I'll try. 40 root 3 divided by 9 plus 4 root 3. Okay, that's the critical value. The area function, the slope of the tangent line, the function at that critical value is 0. But that has to be, this has to be here. The critical value has to be a minimum. It can't be a maximum. So you cannot maximize the area function at that critical value. You can only minimize it. So that means then to determine where the area is maximized, you have to evaluate the endpoints. You have to evaluate the endpoints. In other words, the maximum value of the area is going to occur at one of the endpoints. And it turns out it's going to be the right endpoint when x equals 10, because what I do here is I evaluate the area when the cut is like there is no cut. In other words, basically A of 0, I want to say this the right way. Hold on. A of 0 would be where like A of 0 when X is 0, that means, based on the picture, right? We had, based on the wire, the first part was X, and then you make the cut, and then the second part here is 10 minus X. So if X equals 0, then you're using all the wire to make the triangle, right? If X equals 0, then that means 10 minus X, this part here, would equal 10 when X equals 0. And so in that case, you're using all the wire to construct the triangle. On the other hand, if X equals 10, then the 10 minus X equals 0, and X equals 10. And so in that case, you're using all the wire to construct the square. So the maximum area is going to occur when X equals 10 meters, because if you evaluate A of 0 and evaluate A of 10, the extreme value occurs at the right endpoint. Remember, extreme values can occur either at critical values, okay, or they can occur at one of the endpoints. And here's an example where it occurs at the right endpoint. So Zoe's right. We do not need to find the area of 4.3 because you're not going to be, in the problem it said, how should the wire be cut? Well, maybe the wire should be cut. If you want to have the most area, don't cut the wire at all, and just make the wire into a square. Let me see. Ian says a circle of 10 meters will have 7.96 square meters of area. Well, that's right, Ian. But what we're doing here is we're gonna either make a square, or we're gonna make an equilateral triangle, or we're gonna make a square and an equilateral triangle. We have 3 options, and the option that maximizes the area is to just make the square out of the wire. See, they're not, that's actually, and they're not allowing us to make a circle. But I think that's very good on your part to sort of notice that. I didn't even think about that. Circles are cool. I agree. Well, you're going to like it when we get to in calculus 2, when you get to polar coordinates. You're gonna like that, because that deals with circles. Okay, are there any questions on that? So the maximum area occurs when X equals 10 meters and all the wire is used for the square. Now, last comment then, the minimum area would occur if you made the cut at X equals 40 root 3 divided by 9 plus 4 root 3, right? That should be a 4. Hold on. So, I don't know why you would want minimum area, but maybe there are applications where you do. Maybe there are. I may think this is a really kind of a fascinating, there are definitely times where you want to minimize things. You want to minimize cost, for instance. Okay. you know, again, there's a whole variety of problems dealing with optimization, a whole variety. It's such a fascinating topic, and again, it's one that that you couldn't really study until without knowing calculus, but now you can study it, and it's really opening up your world. You see, definitely opening up your world. Are there any questions then? Or are there any? All right, I'll stop the recording.